We just saw an example of a classification tree. Just a nice simple example. And so in this case, these xi's were in R2, our data, and the yi's were in just 0, 1, so this is a simple binary classification case. And in this video, we're going to explore a regression tree, just a simple example. And so for our regression tree example, we'll just take a super simple case where the xi's are just real valued and the yi's are also real valued. So that's, you can contrast that with this. And this is sort of oversimplification, taking the x's just to be real valued, because we don't have to choose, we don't get to choose different coordinates to split on, but at least I can draw an example in this 1D case that we can visualize. So let's see here. So let's look at, say our data is, now we get some data that looks something like, so just to be clear, so this is the x-axis and this is the y-axis here. So let's say our data something like this. I don't know, maybe we get a point here, something like that. And then it sort of goes up maybe something, and then we get some other stuff here, and then maybe some stuff here. I don't know, something like this. So maybe this is our data. So each of these points is an x in our training data. So remember, we have our training data where we have these sequence. So each of these points is one of these x's and one of these y's. So each point has an x and a y. And now, just like before, so we constructed this tree, this binary tree. So remember, our general approach for a classification or regression tree is we're going to construct a binary tree, and we'll minimize the error in each leaf. So let's decide how we're gonna, we'll just choose some tree here, just some arbitrary. Later we'll talk about how to choose a tree in some good sort of way. But so say we split here first, so we divide the x's into all the ones on this side and all the ones on this side. Looks like a pretty good split. Now over here, this looks like a pretty good split, so let's split there. And now this one's a very nice split. And not so clear here, maybe we'll do something like that. So this defines a tree, just like before. So let's say, I don't know, this is maybe like 1, just to make our life simple. 2, maybe this is 2.8, maybe this is, I don't know, 3.5 or something. So what's the tree that corresponds to this? Well, just like before, so you can imagine it just exactly what we're going to do here. So we have our, so is x greater than 2? That was our first split. And we have either yes or no. And if it's no, then we have a split here. So we have, is x greater than 1? Yes or no. And then, so let's take the case when it's less than 1. So here we have all these points, and remember before we counted the number of each class in each leaf, but we can't do that because we don't have classes. We just have these real valued numbers. But our general strategy is to minimize the error in each leaf. So we will choose, let's choose some error. So the error that we will use is the squared error. So we're going to choose a y hat. So we're looking at this region, and we're going to choose a y hat for that region that minimizes this. So let me call this region, I don't know, R1 or something. So R1 is this region, and if I is all the indices of the points that lie in this region. So I could have also said here, so this is all the i's such that xi is less than 1. And it also happens to be less than 2, but this implies that. So we want to minimize this error, and it's pretty easy. If you just differentiate this thing, you can check that this is minimized. You differentiate it, you set it equal to 0, do the usual calculus thing. Set it equal to 0, solve, and you take the second derivative, verify that's a minimum, and what you end up with is that y hat, so I can write the argmin of this over y hat is, well, let me say it this way. So we want to minimize this over y's, and if y hat is the minimum, then that implies that y hat equals the average of the yi's, in this R1. So this is the minimizer. So we're going to take this error and we'll minimize it in each leaf. So in this leaf, we get some y hat over here, which is some value. Looks maybe something like that. That looks like about the average of all these y's. So, and then maybe here, so I don't know, what's that, like maybe 0.2 or something. And then here we get the average of the y's in this region. Maybe we call that R2, so we average those. And then we average the y's in this region. So maybe, I don't know, what was this? We said 0.1, maybe this is like, I don't know, 1.1, something like that. So 1.1 when it was less than 2 and greater than 1. And then we have to continue our tree here. This is, let's see, so what did we do next? We did 2.8, so is x greater than 2.8. And we can go, if it's less, we can just finish. That was, I don't know, 0.5 or something. This one here, and then we get another one here. So let's go down here, and then we have one more split, which is 3.5. Yes and no. That was no. That was yes. Yes, no. Yes is, I don't know, like 2 or something, and no is like 1.5, something like that. So in each leaf, we take the average of the yi's that were in that leaf, in that region. So this defines a binary tree, and the training error, that is the error on the data that we got to observe, our training data, is minimized in each leaf. So there are some, we're not getting these all exactly. In fact, we might not get any of them exactly, but we're minimizing this sum of the squared distance from each of these points to this value. So this is like the minimizer for that. Oh, and this one too. So this is a regression tree, very simple, maybe even simpler than the classification tree. And in a little bit, we will see how to construct both classification and regression trees to get some, rather than just sort of this arbitrary thing, to get good performance. So here, let me just point out this resulting function. We get this function f of x. So in a classification problem, we always get a function f of x, and this function is piecewise constant on these regions. And more generally, it'll be piecewise constant in some regions that are defined by the binary splits in some higher dimensional space.